Assalamualaikum warahmatullahi taala wabarakatuh. Okay, so last time we have discussed about the entropy of the measure preserving transformation, and we also discussed about the conditional entropy with respect to the pre-image of the partition. Okay, so today we will continue. Last time we stopped at the limit, right? Limit of the entropy of the joint pre-image. So let us recall the entropy. So we have the entropy of psi is equals to this formula. Mu of AK log mu of AK. So this entropy is positive. So we let T be the measure preserving transformation and psi be the finite partition that consists of A and element. Okay, so we have the join of the partition with the pre-image of the partition is given by this element AK intersect A T inverse of AL, where K and L runs from 1 until n, and the joint partition of 3 P is given by this element AK intersect T pre-image of AL intersect with second pre-image of EM, where K, L and M also runs from 1 to until n. So in general form, we have the joint partition from finitely many partition until M of the pre-image of the psi is equals to this partition joined with the inverse, the pre-image of the partition, joined with the second pre-image of the partition, joined with the third pre-image of the partition until the pre-image of M of the partition. Okay, so here the total element here is n power m or less. Okay, so in the case of the partition, we would like to find the entropy of the joint partition, finitely many joint partition that is given by this. So what is the entropy for the finitely many joint partitions? So we will have the limit. So we write okay. So we write the entropy of the measure preserving transformation with respect to the partition is given by this limit. This m goes to infinity of the entropy of its joint partition. Okay. Okay, now let's consider example. So we let X be this segment 0, 1 and M be a usual Lebesgue measure. Okay, so we have the T, which is the major preserving transformation of dyadic. So we have Tx is equals to 2x in mode 1. Okay, and we have the partition is given by these two elements. So I have 0, half, half to 1. Okay, and let's try to find the pre-image of this partition. So in previous example, you found already the pre-image of this partition is you have how many? 4, right? You will have four segment. So I have 0 to half union with half and 3/4. And another one, you have 1/4 and 1/2 union with 3/4 and 1. Okay, so this is the this we call it as the pre-image of the A1. This is A1, this is A2, and this is the pre-image of A2. Okay. Any questions this part so far? No.
No.
Okay, good. So we move on. Okay, next slide. So I have, how can I find the partition psi union or join with the partition, the pre-image of the partition. So you will have, so according to your psi dengan pre-image tadi, okay, psi and the pre-image. So if you want to find the join between these two, you have to find the what? Intersection, right? So A1 intersect with this, A1 intersect with this, and A2 intersect with this, and A2 intersect with this. So you need to find the common elements. So the join you will have 0 to half 1/4, and then you will have 1/4 to 1/2, and then you will have 1/2 to 3/4, and then you will have another one 3/4 to 1. So you can check. Okay, you can check later. Okay, so this is the join. Okay, the join of the partition and the first pre-image of the partition. So what about if you find the second pre-image of psi? What will you have? So the first one, okay, so the first pre-image you have 4, right? You have this one, 0 half union with half 3/4. And the second A2, the pre-image of A2, you have 1/4 and 1/2 union with 3/4 and 1. So now you find the second pre-image, which is the second pre-image of the partition. So you have to find the pre-image of the
Bukan 0 to 1/4.
yang mana? Yang mana?
Pre-image.
Oh yes, 0 to 1/4. Correct. 4. Yes, 1/2, 3/4. Yes, 1/4, 1/2. Correct. Okay. So nak cari the second pre-image of this. So you have to find the pre-image macam kita cari sebelum ni. Okay, kita cari dan example tu, kalau tak nampak boleh lukis graph. So I would have 8 elements, because here 0 until 1/8 union with 2/8 dengan 3/8 union with 4/8, which is 1/2, until 5/8 union with 6/8 dengan 7/8. Okay, this is the first. Ni A1. Okay, and then you will find the second part. You will have 1/8 dengan 2/8 union with 3/8 and 4/8 union with 5/8 and 6/8 union with 7/8 until 1. So this is for the second pre-image of A2. Okay. So yang ni kita kena, kalau tak nampak boleh lukis graf macam sebelum ni. So you will have so if you go further, okay, cari lagi. So you have psi join with the first pre-image, join with the second pre-image. So using the pre-image punya property, so you will have psi join with the first pre-image is join with the second pre-image. Okay. And kalau so is psi, this one psi join with the first pre-image, you will have tadi lah. So this is actually equals to 0, 1/8 if you tu dia punya order susun, and then I have 1/8, 2/8 until 7/8, 1. Okay, so you will have 8 punya elements, because okay, first you find the first pre-image. Okay, jap saya tunjuk kat sini. Okay, first you find the first pre-image. So the partition, you have this one, and then you find the first pre-image of the partition. So you have these these pre-images. Okay, and then you join. And then you join, you got 4. Join meaning you have to consider the possible intersections, betul? Now, you go for the second pre-image of the partition, so you will have these two elements. Okay, and then you consider the join, meaning you have to consider all the possible intersections between this. Join ni dengan ni. Join of the side and first pre-image dengan the second pre-image. So you will have 8. Actually they are kita gabung saja. Kita gabung and kita reorder dalam bentuk set. Okay. And then what do you do? So actually this is, I can put this in general form. I can write this way. So I can write as I/8 I plus 1/8, where I runs from 1 until 7, 0 until 7. Okay, so we go for induction. So what about if we join many steps, or many steps of pre-images? So we have t minus 3, t minus 4, and so on. So how we want to prove this? So we use the popular mathematical induction. Okay, by induction, so I have this form, the join from k and from 0 until n minus 1, t or to the power of minus k of psi is equals to. So we can put in general form. So kalau kita tengok in general form, kalau join 1 kita dapat 4. So sekejap here. If you psi you got 2. If you pre-image one step, you got 4. And you pre-image with 3 step, you got 8 and so on. So what can you infer from this pattern? So I can write I over, so kalau kita pergi K step back, cari pre-image dia, it's 2 power something kan. So the general form 2i plus 1 okay. Oops. Mana tadi? Number theory. Sekejap dia dah hang, lepas tu dia dah okay. So kita continue sekejap. Okay.
Dah nampak dah.
Nampak dah? Okay. So in general form by induction, I can write the general join of the pre-image of the partitions. So kalau tadi, kalau first step kita dapat 4, kalau 2 step kita dapat 8 and so on. So dia macam 2 kali ganda kan. So you can write this as I plus 1 over 2 power m. Dia punya elements in the join partition. So I have, I runs from 0 until 2 power m minus 1 in general. Boleh faham tak kat sini? So
Boleh.
if you, yes, if you, okay good. If you do more, t power of minus 3, you will get 2 power 4. Maksudnya ada 16. And then you go further, you can have, so then you can have this formula, general formula. So from previous calculation, I know H of the side or the entropy of the partition. So tengok partition tadi adalah symmetric. So the values of the symmetric partition, kalau dia ada 2 elemen dalam tu, dia berapa nilai dia? Log
Yang
berapa?
mana tu?
Ni entropy. Entropy of the
Log
partition. Log 2, correct. So log 2. Okay. So kalau nak cari entropy of the join partition tadi, so you have psi join with this one. This is, I think you got log 4 in previous lecture. Okay. Thus, what can you say? So thus you can have the entropy of the psi join with the first pre-image, join with the second pre-image, is equals to
Log 8.
log 8 andai. Dia ikut pada number of elements dalam the partition. Sebab dia simetrik. Okay, so log 2, log 4, log 8. So you can guess what happen if you take more and more steps of the pre-images. So you will have berapa? So entropy of I could say, therefore entropy of the join T minus K of psi is equals to log,
2 power of m.
correct. So this is log 2 power of m. Okay, now you found already the entropy for the joint. So now we want to use the limit because this is with respect to, ini hanyalah entropi dekat joint saja. So tapi kalau kita nak cari entropy of the major preserving transformation with respect to the partition of this one. So that means you have to find the limit. The limit of m goes to infinity of this entropy. Join. Okay, so how to find this? So you know the limit as m goes to infinity, I have 1 over m. So this is the value for the ni tadi adalah log 2 power m. You found already in the previous calculation. So I can put the value here. So I have log 2 power m. You simplify the calculation. I have 1 over m. So here we use the properties of log. So I can bring this m to the front. So this become multiply with m log 2. And you can cancel out this m. And since our limit now doesn't depend on m already, so what's left?
Log 2.
Log 2 only. Okay, so that means your entropy H of psi is equals to the entropy of the T, or relative, we call it as relative entropy with respect to the partition, is the same. Given that, so you have the, given that your properties in there here, dia punya properties tu kena symmetric, dia punya values join dia tu ada pattern, itulah. So kalau the question ask you to show that this entropy of psi is equals to the entropy of the relative entropy, which is relative entropy of the major preserving transformation with respect to the psi, so you have to show that they are the same. Macam tu. Okay. So for dyadic transformation, yes, you can have this the same, because dyadic ni macam special transformation. So kalau you choose another transformation, for example T ni can be Bernoulli ke triadic. Triadic meaning ada 3 ni lah, 3x bukan 2x. So kalau ada 4x, 5x, 10x for example, so what happens to the value in the relative? Also different. So kita boleh cakap kalau triadic berapa agak-agak dia punya tu, triadic. Yes, log 3. Okay. Kalau triadic log 3 lah. Dia relative. But you need to show. Okay. Alright. We have another last one example, and then before we start new topic. Second example, we consider Bernoulli. Let's try to consider Bernoulli shift. Okay, Bernoulli shift defined on this segment 0, 1 to this set E, and you have the measure. So measure of 0 is P1, measure of 1 is P2, where we consider the probability measure. P1 plus P2 must be 1. And you have the partition function I from 0 until infinity of EI, where EI equals to 0 for any I. Okay. Let us define the partition in the Bernoulli. Maksudnya define partition in the Bernoulli. If you remember, we have the cylinder coordinate, right? Cylinder punya tu coordinate function. So I have the element in the partition could be x0 omega is equals to 0 in the first digit, and the second one at 0 omega is equals to 1. Where x0 omega is equals to 0, meaning that omega is taken from the whole omega, x0 is equals to 0. This is the definition. The coordinate function. Okay, now let's find the pre-image of this partition of Bernoulli. So I have the pre-image of psi. So kalau pre-image macam mana? This is major preserving transformation. So the pre-image is given by. So this one I think you need to check your previous notes. So kalau pre-image selalunya kalau psi tu adalah x0, betul? The first coordinate. Kalau dia punya pre-image, dia punya jadi second coordinate x1 lah. The pre-image. Ni jadi kalau previously psi you have at 0 kan? At 0. So kalau pre-image dia terbalik lah. Okay, you need to check your notes. Okay, let's assume that this is the pre-image. Okay, you check already. So this is correct. So I have the pre-image is given by these elements. So now I want to find the join of the pre-image of this partition. So you need to consider all the intersection. So I have intersection this one x0 omega equals to 0 and x0 omega equals to 1. So intersect. What do you have? Kalau intersect, that means you will have two coordinates lah. So I will have x0 omega equals to 0 and x1 omega equals to 0. Macam kita divide 0, 1, kita potong lagi first digit, second digit, ingat tak?
Ingat.
Yang tu 0, 1 and then you divide lagi. So ini becomes 0, 1, 0, 1 and then you divide lagi 0, 0, 0, 1, 0, 1, 0, 1 and so on. Macam tu. Okay. Next, I will have x0 omega equals to 0. x1 omega equals to 1. Another x1 omega equals to x0 omega 0, 0, 0, 1, 0, 1, 0, 0, 1. x1 omega is 0 and then x0 omega is 1, x1 omega is 1. Okay, this is the elements. So now we would like to find the entropy. So entropy of this psi, entropy of this partition is given by, kalau Bernoulli kita kena ikut Bernoulli lah, maksudnya minus sum of the mu tu kan, minus maksudnya akan jadi minus P1 log P1 minus P2 log P2. Is that okay?
Okay.
Okay, this part Now entropy of partition, no problem. Now entropy of the joint. Entropy of the joint. What would you have? So first you found already the joint. Okay, now find entropy. So entropy ni kena cari satu-satu lah, kena tambah semua. So dia punya after using that function ni, so dia akan dapat P1 darab dengan P1 log P1 darab dengan P1. Okay. So I will have ni after dah simplify ni. Minus P1 P2 log P1 P2 minus P2 P1 log P2 P1 minus P2 square log P2 square. Okay. And simplify. You will have P1 P2 dengan P2 P1 sama tak?
Tak.
Sama.
Tak sama. Sama ke tak?
Tak.
Okay, let's simplify ni dulu. So simplify log ni dapat apa? You can bring this two kan? To power P1 square ni you can bring in front. So I have minus 2 P1 square log P1 minus P1 P2 log P1 P2. Okay, minus P2 P1 log P2 P1 minus, so again kita simplify yang last one ni, kita akan dapat 2 P2 square log P2. Okay, sampai sini okay? Okay, now
Okay.
kita boleh, alright, let's try to combine. Kita collect. Sebab log P2 P1 P2 P2 P1. So ada lagi boleh kita simplify? Boleh. Minus log P1. Yang ni kalau log P1 P2 apa maksud dia? Maksud dia macam log P1 dia macam ni. Log P1 tambah log P2 tu tak?
Betul.
Okay, so you can simplify that. Okay, let's simplify to log P1 minus P1 P2 log P1 minus P1 P2 log P2. Boleh? Saya pecahkan ini pada 2. Next minus, oops, aduh hai. Okay, minus mana ni? Cuba buat. Sekejap, saya punya laptop panas. Pagi tadi dah ada kelas. Okay, and then simplify ini juga. So I minus P2 P1 log P2 minus P2 P1 log P1 and then minus 2P2 square log P2. Now you can collect all of siapa yang log P1 kumpul duduk P1, log P2 kumpul duduk log P2. So I have, so after kumpul ni I have what? Okay, P1, P2 log P1 dengan P2, P1 log P1 sama tak? This and this. Are they the
Sama.
same? Sama. Sebab dia orang just tukar 3/5 log 6 dengan 5/3 log 6. Sama. Okay. So kita boleh kumpul. So I have simplify minus 2 P1 square plus P1 P2 log P1 minus 2 P2 square plus P2 P1 log P2. Okay, agree?
Yes.
Alright. Okay, next. Simplify. So this dalam ni ada lagi P1 dengan P1. So you can collect them. So P1 P1 plus P2 log P1 minus 2 dengan P2 factor out P2 plus P1 log P2. Okay. So notice that in Bernoulli, what is the value for this?
One.
1, correct. So this is 1. So this is 1 and this is 1. So jadi 1 akan, so the last what you can do, you will have, saya ulang balik, minus 2 P1 plus P2 log P1 minus 2 P2 and P2 plus P1 of log P2, and then this is equals to 1, this is equals to 1, so I have minus 2 P1 log P1 minus 2 P2 log P2. So what is, can you see what is the value here? Ni sama dengan apa? Ingat tak tadi kita dapat kita punya apa? Entropi tadi. For Bernoulli, I have minus P1 log P1 minus P2 log P2. Betul? So untuk this one, the joint I have, what is the entropy? 2 minus what? Minus 2 darab dengan semua benda ni kan?
Kenapa minus 2?
Dapat minus 2 P1 log P1 plus P2 log P2. So macam kita darab dengan minus 2 of the entropy. Agree tak?
Kenapa
Boleh?
darab minus 2 tu?
Kenapa darab dengan?
Bukan
Kenapa darab dengan? Tak perasan mana dapat minus 2? Ke apa? Ni.
Kan
Yang ni.
entropi side minus P1 log P1.
Ni. This one is the entropy of the partition. Okay, entropy of the partition, you have this minus P1 log P1 minus P2 log P2. Kalau entropy of the join yang ni, you got minus 2 P1 log P1 minus 2 P2 log P2. So if you factorize minus 2 here, betul, you have P1 log P1 plus lah P2 log P2, betul?
Betul.
Okay, so if I write this, they are the same, and then I should get, bukan minus 2, I should get two entropy. Betul tak?
Betul.
Okay, so betul lah, ini adalah, this is the final one. Okay, so that means tak ada negatif lah kat depan tu, sebab negatif tu dah ada dalam entropi ni. So that means as conclusion, the entropy of the join with the first step here, the pre-image of the partition is double of the entropy. So kalau kita cari entropy of the three partition, for example, you can guess lah. Okay, pre-image of the first pre-image junior the second pre-image. So agak-agak berapa?
3
entropy of side. Okay, dia triple. So kalau join lagi 4 partition dapatlah 4 and so on.
Doktor, P1,
Ya.
P2 apa semua tu V dia tak perlu uniform kan?
Tak perlu. Untuk case ni, example ni we don't specify what is the value for the Bernoulli measure. Ni kita tak specify pun. Maksudnya kalau kita tak specify, kita boleh dapat value ni. Tapi but I'm not sure. But I cannot say if kalau P1 dengan P2 ni, let's say if you consider 2, 1/2 dengan 1/2. So maybe you can have this uniform, you can have the calculation macam ni. Tapi kalau lah let's say you consider 1/2 and 1/3 and 2/3 for example. So the summation is 1. Okay, so if I check this, maybe the same. Maybe the same. Because we can sebab nanti kan kita akan cari kalau trigger, maksudnya log P1, P2, P3, so ni become cube, sama je. So it doesn't matter. It doesn't matter kalau Bernoulli measure ni, it doesn't matter kalau dia simetri ataupun tidak, you can get this. Tapi kalau Bernoulli measure tu, satu dia bagi kosong, satu dia bagi 1/2. So the measure 0 plus 1/2 is 1/2 kan, so it cannot be 1. So meaning that we cannot apply this kind of calculation to get the general entropy untuk yang ni. Sebab dia punya measure tu tak sama dengan 1, dia kena 1. Okay, any questions until this part?
Tak ada.
Tak ada, alright. Okay, good. So we finish our last lecture about the entropy of the joint. So now we move on to new topic. Okay, lecture 12. Ni baru masuk lecture 12. Kolmogorov-Sinai theorem. So Kolmogorov ni Prof Nasir punya supervisor. pure mathematician, power man. So let this triple, okay, be measure space. And T from X to X be measure preserving transformation so for any A in the sigma algebra, so for any A in the sigma algebra, where did I write somewhere? Okay, dah hilang. Again, sekejap. Sorry. Saya tulis balik Kolmogorov-Sinai theorem. Let X, F, and mu be a measure space and T from X to X is measure preserving transformation. Okay, let for any F for any A. Kenapa terbalik? So for any A in the F, okay, so I have measure the pre-image of the set is equals to measure of the set. So this is the definition of what? Ini.
Measure preserving.
Okay, measure preserving transformation. So what is Kolmogorov-Sinai theorem is about? So what is the entropy of the transformation? So now we go to the HT, small h. First, for any partition, finite, measurable partition, we define entropy as the following sum. Entropy of the partition is given by this formula. So minus sum from of I from 1 until n mu of AI log mu of AI. Positive, non-negative. Okay. If the partition less than or equals to the second partition, where the second partition is given by this element, then Then I have the entropy of psi is less than or equal to the entropy of eta. So ni macam kita recall balik, tak masuk lagi Kolmogorov-Sinai theorem lagi ni. Kita baru recall balik the entropy punya properties. So the first properties, kalau kita ada all this major preserving transformation in the major space, I have the finite partition eta and also psi, and both are finite. So the entropy is given by this formula. So if we have the psi is less than or equal to eta, then we have the entropy also implies for the entropy. So that means entropy of psi also less than or equal to eta, the entropy of eta. So properties number 2, the relative entropy, meaning the entropy of the major preserving transformation with respect to the partition is equals to the limit of m goes to infinity 1 over m multiplied with the entropy of the joint, finite joint. Okay. I. Okay. And limit exists. If the limit exists, the limit that means it's either finite or infinite. Okay. Next properties number 3, entropy of the major preserving transformation. This is equal to the supremum with respect to psi of the entropy of the relative entropy. So we call it as supremum of the rest. So I would say this is actually the overall finite partitions. Tahu maksud supremum? Ingat tak maksud supremum? Infimum supremum. Dia maksimum tapi dia tak. Yes, dia almost to reaching maximum but not reaching. Dia macam ni. Kita let's recall what is infimum, what is supremum. So kalau supremum, so kalau maksimum, saya tengok maksimum dulu. Kalau maksimum, this is any finite, any infinite set, okay. Maximum maybe ada, maybe tak ada. Okay, maksudnya we should reach some value here. Okay, dia ada maksimum setakat tu sampai situ. Kalau supremum, dia adalah least upper bound. Okay, you have the upper bound, lower bound, betul? Upper bound macam kita ada satu garis. Okay, lower bound, upper bound. Ni upper bound. So least upper bound dia sampai sini. Least upper bound. Sorry, terbalik. Ni upper bound. So kalau upper bound dekat sini, so list dia adalah not necessarily kita reach the value. Tapi dia ada list upper bound, dia ada paling kurang, macam mana nak cakap? Paling kurang dia ada dia lepas satu value. Itu macam mana nak cakap?
Infimum kan?
Itu infimum. Do not have kalau contoh kalau you have a set Y, let's say you have set Y 0 and 1, okay, you have a segment 0 dengan between 0 dengan 1. Kalau supremum of Y is 1. Upper bound dia tu dia boleh paling jauh dia pergi 1 tapi dia tak reach. Dia tak boleh reach. Sebab dia kalau segment kan 0 1 tu dia open segment. Dia bukan close segment. So dia memang dia boleh reach 1 tapi dia takkan sampai, dia tak boleh touch. Supremum of Y maksudnya 1. Upper bound dia adalah 1. Least upper bound. Okay, yang penting macam ni. Maximum you should reach some value. You should reach. Okay, you should be there. Kalau supremum, you may not reach the value. Sebab kosong, kalau in segment 0, 1, you cannot have maximum. Betul tak? Betul. We cannot have maximum in this set. Mesti akan ada satu value yang sama dengan satu, almost reaching 1 but cannot reach 1. Itu beza maximum and supremum. Okay.
Doktor,
Ya.
yang relative entropi T dengan apa nama dia? Psi dapat list.
Dapat list?
Ya ke?
Tak faham. Macam mana soalan?
Yang nombor 2 tu kan? Yalah, property nombor 3, supremum of tu relative entropy T dengan psi. Maksudnya relative entropy T psi tu dapat list.
Ya. Dia entropy of T dia can equals to the supremum sebab dia maybe not, macam ni, dia tak boleh sampai exceed this supremum. Least upper bound. Dia entropy, maksudnya entropy of the major preserving transformation equal to the supremum of the set. Kalau H relative entropy with respect to the partition adalah some value kan, log 3. So log 3, contoh log 2 ke log 3, log 4 tadi. So dia punya the whole entropy of T is equals to the supremum of log 3, log 4. Apa supremum tu? Supremum. Macam contoh tadi lah, Y 01 kan, supremum of Y 1. Kalau log 3, contoh yang ni dapat log 3, HT is supremum of log 3 maksudnya berapa? Log 3 lah. Dia almost nak pergi ke log 3 tapi dia tak reach. Tu je. Tapi maksimum memang kena boleh, tapi kalau supremum tak boleh. Supremum. Maksud supremum. Nanti kita tengok dia punya example. Okay, first case. Let X be arbitrary. T is identity. So IDX is the function that brings you X to X sebab dia identity for any X to X. Okay. Let psi be any finite partition. So if I find the pre-image of the identity function, identity partition, so what do you have here?
Identity.
Identity, kalau identity, kita ada partition, kita ambil pre-image of the partition identity. Identity, dia punya psi lah. Okay. So kalau if you ambil the second pre-image of the partition identity,
X.
akan dapat psi balik lah. Sebab identity kan. Boleh faham tak?
Oh.
Okay.
Okay.
T tu adalah identity transformation. Tu ID tu adalah kita punya T. Okay. Okay, so kalau in this case, what do you have? Kalau kita ada I punya steps, I punya pre-images, so still you still get the same lah. You still get psi. So take the join of this identity transformation, okay, of the partition. So I will get the same partition psi. And you take you want to find the relative, okay? So now the T become identity, ID, with respect to the partition. So I have, using the formula, the limit. So I 1 over K of the H with the join. It was 1 ID of psi. This gives you the limit of K to the infinity 1 over K. So kalau join dapat apa? Entropy. H of what? H of psi. Because identity, join je identity, still you can get the same. So kalau yang ni akan jadi apa? As the limit of K goes to infinity, 0. Yes, you will have 0. In conclusion, I can say the relative entropy of the transformation identity with respect to the partition psi is equals to 0 for any psi that have this for any psi. So that means your entropy of the transformation is equals to what? Supremum of the psi equals to H of ID and psi, which is supremum of this is 0. So supremum, the things that the lowest it can go is
0.
0. Cannot be negative kan? Okay. So that means you got 0 for identity transformation. Contoh. Next, another contoh. Another example. Let's you have a finite set again. Then you have the entropy is 0. Entropy of the transformation is 0. So I let V is be trivial punya element, which means that it has the whole set. So this means that your V here, the partition V here is less than or equal to psi. So this is the minimum. the V here is the minimum and the V here is this because it is the smallest. This macam mana cakap? The smallest partition it can be is V, the trivial. Sebab okay, let's say this is partition 1. Kita define another partition, okay. I call it as epsilon. Again, epsilon is the set that has X for any X in X. So this means that the set here meaning the any set that has consists of single point. So I call this as partition number 2. Let us define V dengan epsilon. So V ni the whole X. Okay, the whole X. So kalau epsilon ni adalah any element that consists of single point. Okay, different tau. So memanglah V tu less than or equal to psi. Kalau psi tu ada dua elemen, V ada satu elemen. Faham? So V less than or equal to psi. Okay, next one epsilon ni kita define as the set, the partition to be the element that consists of single point. So it can be anything. Okay, now so one point here, if X is this segment is between 0 and 1 and epsilon is this segment, consists of these elements. So how many elements do you think that has in this epsilon? Finite ke infinite?
Infinite.
Infinite, yes. So that means infinitely many elements. Because X can be anything in this between 0 and 1. So there are infinitely many elements in this epsilon. So in our case, we only consider only finite partitions. In our case, we consider only finite partitions. So kalau nak define, kita boleh define the finite partitions to be next one. So if X is a finite set, then epsilon is a finite partitions. So kita tak boleh nak define the second partitions epsilon to be macam ni because there are infinitely many. Kalau kita nak define dalam X, maksudnya tak boleh sebab there are infinitely many elements in this partition. Tapi kita boleh define in some other way. Contoh, kalau nak jadikan epsilon ni sebagai finite partition, you can define X as, let's say ABC. Okay, you have these three elements in the set X. So kalau epsilon, that means what is the element in the epsilon? In the partition epsilon?
ABC.
Okay, A, B, C. Sebab kita nak kita define epsilon to be the elements that consist of single point. So kalau kita define X to be X, A, B, C, so that means A has epsilon has 3 elements dalam ni. So finite. Okay, so that means this is the largest partition. So kalau X yang V is X tu, so this is the smallest. Kalau X ni adalah yang sama ABC sebab dia ada satu saja. dalam tu, the whole X. So the largest partition is epsilon. So kita define this macam apa? These two types of partition so that we can modify a bit the to find the entropy. So if you have the psi is given by this formula AB dengan C. So I have, let's say, I call this gamma. So gamma ni must be less than of psi, must be less than, bukan gamma, V. Epsilon. So you can define any function, any partition in the middle between V dengan epsilon ni. Sebab the largest would be V, which is the trivial punya partition, and epsilon would be only the partition that consists of single element. Yang tu je. So for any partition, you can have this condition. I have this. So kalau X kita finite, so our epsilon finite. Kalau X, our X is infinite, that means our epsilon also infinite. It depends on the X for the case of largest partition. So since we only consider the finite case, so and since this is finite, then I have the entropy of psi is less than entropy of the epsilon. So kalau finite baru kita boleh compute entropy of the epsilon ni. Kalau tak finite tak boleh compute. So from this you can have, if T is MPT or major preserving transformation, I have psi joined with the the pre-image would be less than epsilon, and the join of these partitions must be less than epsilon. This implies that your entropy of the join, entropy of this join T minus I of psi must be less than or equal to the entropy of the epsilon, since entropy of the epsilon is the largest one. So for the case of join, okay. Next, for the case of the relative, using the formula, the limit over K, H of K I 0 until K minus 1, T of I psi. So I have, so since I can write the entropy here, since there must be non-negative, right? So the relative entropy is between 0 and from our first property, that is this one. We have that 0 is less than the relative entropy will be less than So the limit less than or equal 1 over k of this. And in fact, this is equals to 0. Which inferred 0 is less than the so that means the between kita akan dapat ni equals to 0. So H the relative entropy also 0 for any psi, which implies that our entropy of the transformation also 0. This one. Boleh?
Boleh.
Okay. So for this case, we have already considered a join. So the join, we have the supremum. So if we have two, the largest and the smallest, okay. So if we have the largest and the smallest, we want to show the left must be less than or equal to the right, and then we have the second, the relative entropy, and then the entropy of the transformation. And we consider the identity transformation, so they are actually equals to 0, and we show that for the identity transformation, the relative and the entropy of the transformation is the same. So for the finite case also, if we have to consider the largest, the smallest partition, and then the largest partition, so the largest partition should be in finite form, finite set. So if the largest is the finite set, so that means we can find the entropy. So we can define the entropy of X to be finite given by this definition. So according to the properties of the entropy, so we have that the smallest must be V, and then the largest would be epsilon. So for any finite partitions, we can have this condition. And that means that our entropy of the partition must be less than or equal to the largest one, which is the epsilon. And we show that for the case of major preserving transformation, we also found that the relative entropy also equals to 0. Okay, so any questions until this part?
No question.
Okay. Mana pergi Komodoro Sinai ni? Okay. Do we have any? Okay, we have another 10 minutes. So for conclusion, how to compute entropy for any major preserving transformation? First, you must have the triple, which is the measurable space, measure space. You must have the transformation Tx from X to X, and must be measure preserving transformation. And for any A in the sigma algebra, that means I have the measure of A, measure of the pre-image of A must be equal to the measure of A. And then you must have the partition finite. Okay, and you can find the join psi, and then psi with the pre-image of psi, and then psi with pre-image of psi and the second pre-image of psi and so on. Okay, this is and we found that this is a sequence of non-decreasing finite partition. Sequence of non-decreasing finite partition. So I have psi must be less than the joint of the pre-image, must be less than of the joint of the first pre-image with the second pre-image, and so on. Must be less than until the V lah, which is supposed to, where this box is actually equals to V of I from 0 until k minus 1 t of minus I psi. Okay, so we call this as sequence of non-decreasing finite partition. Apa maksud non-decreasing? Non-decreasing, increasing lah, tapi dia tak berapa, dia tak increase. Increase maksudnya dia strictly increase. Ni non-decreasing is too small. Dia increase kecil-kecil je tak nampak.
Dia boleh jadi sama kalau
Yeah, correct. Sebab kalau non-decreasing dia ada inequality here ni, dia ada equal sign. Kalau increasing, strictly increase, dia 1, less than 2, less than 3, less than 4 and so on. This is strictly increasing. Okay, non-decreasing meaning ada equal sign, they can be the same. Okay, any questions until this part before we end our class?
tak ada.
No. Alright. Okay, so I end this class. We have finished first part of lecture 12. So on Thursday we will continue with the definition of generator. Again, we will consider the join and the pre-image of the partitions and consider some of the examples. Okay. Alright, class. Thank you for your patience and also for your attention. So insyaAllah see you on Thursday. Okay, Assalamualaikum warahmatullahi taala wabarakatuh.
Waalaikumsalam. Thank you, Doctor.
Okay,
Thank you, Doctor.
Thank you, Doctor.
welcome.